Welcome to this session with Professor Peter Atkins on the theme The Science of a Godless Cosmos. Professor Atkins has been a household name for a science student, especially those in grade 11 and 12, thanks to his iconic textbook on physical chemistry, which inspires a lot of science students of India, including me also, who love the subject. His book is not just a book but an inspiring introduction to the equations and laws of physical chemistry. And still, convention compels me to formally introduce him. Professor Peter Atkins, an emeritus professor of chemistry at the University of Oxford and a fellow of Lincoln College. Professor has authored over 70 acclaimed works, including Molecular Quantum Mechanics, The Laws of Thermodynamics, and Conjuring the Universe. His books, blending science with philosophical inquiry, have earned him global recognition as one of the finest science communicators. His contributions have been celebrated with honorary doctorates, the Royal Society of Chemistry's Murray Medal, and the Michael Faraday Award. The theme, The Science of Godless Cosmos, reflects Professor's vision on a universe governed not by divine intervention but by natural laws, rooted in simplicity and symmetry theorem, Noether's theorem. It's a perspective that redefines how we view the cosmos and invites us to explore its beauty through reason and science. With that, I hand over to the stage Puskar, President of Caucus, to lead this session ahead. Thank you.
Thank you so much, Soumya. It's really quite an honor. And I think I might already be feeling a bit nervous to be interacting with Professor Atkins. For it's been nearly a decade since I started thinking about the question of God and science and considering the prospects of a godless cosmos. We hosted Professor Lawrence Cross a few days back, for instance, and now we have with us Professor Atkins. And the theme for today, the science for godless cosmos, I think is a perfect encapsulation of how Professor Atkins' work, Conjuring the Universe, which, by the way, I think I had mentioned in the invitation that I'd sent to Professor Atkins, provides a simple and elegant explanation for how we may conceive of a godless cosmos without bringing in, as I think Professor Atkins would say, extraneous entities and extraneous explanations. With that having been said, I hand over the floor to Professor Atkins for his brief introductory remarks, following which we'll have the moderated discussion based on the questions that we have prepared. Professor Atkins, over to you.
Well, let me just outline my own position. And it seems to me that there are two ways of understanding the universe. One is to ignore all the evidence, and the other is to take evidence into account. And of course, the religion is all about ignoring evidence and building on wishful thinking and superstition. Whereas science is really, I think it might be better to call it the scientific method rather than science itself. The scientific method relies upon evidence, is driven by evidence, and adapts to the evidence that experiments and observation provides. And it's not only driven by evidence, but it makes sure that the answers that it is groping towards are consistent. And wherever the information comes from, be it from biology, from chemistry, from physics, and so on, all the ideas and concepts must be coherent and not clash with each other. Whereas religion, of course, is famous for the clashes because people invent stories. People in one country invent one kind of story. People in another country invent another kind of story. Because they are irrational, the stories can't be attacked by rational argument. And so the only way of overcoming another view about the nature of God is with the bullet, the flame, or by going to war and eliminating the people who think differently from the way you do. Science, though, is astonishingly international. People don't go to war over science. Of course, they use science to go to war, but they don't go to war over its assertions and concepts. People say that music is international. Well, to some extent it is, although sometimes, to a Western ear, Eastern music doesn't sound very agreeable, and vice versa. But science is more international than music is, because science grows from ideas established everywhere in the world. Quite extraordinary, really. And so science is a force for good in that sense, that it binds people together because they feel themselves in a collaboration. Now, people say that science cannot answer all the questions that are important to humans. Well, some of the questions that it is claimed cannot be answered by science are not really questions at all. They're just inventions. So some people say, what is the purpose of the universe? Now, in my view, the universe has no purpose whatsoever. So why waste time wondering about what its purpose might be? I think it's rather wonderful to think of this extraordinarily cosmos-wide universe, just this amazing entity, huge entity, the biggest conceivable entity, having no purpose whatsoever. I find that rather charming, that thought. And then people say, what about morality? And in my view, religion leads to a variety of moralities, not all of which are benign. Science can understand the origins of ethical behavior by looking into our evolutionary history and to see how what we regard as good has emerged as we have evolved and and formed societies. So let me conclude these introductory remarks by saying that I think there are only two really big questions for science to answer. One is the origin of the universe, how it came into being. And religion, of course, gives the lazy answer. It says, well, God did it. But of course, that is just a confession of ignorance, pretending to be an explanation. So it's a deceit, a lie. And whereas science, think of the progress that it's made in the past 300 years towards answering exactly that question. We're by no means there yet, but such has the progress been in the past 3 centuries that it would be very defeatist to say, well, maybe God did make it after all. So science is on the track of that deep question. And the other deep question of existence, which science is tackling, is the nature of consciousness, and everything to do with consciousness. It's a fascinating question. I think philosophers look at that question and think to themselves, we will never answer it, because philosophers are really pessimists. They try to hold back understanding, sometimes wisely, but on the whole, they invent obfuscation, whereas scientists are edging towards an understanding of consciousness with the development of computation and so on. Whether we will ever really be able to understand it fully. See, I think that there are two different kinds of answers. The origin of the universe will be explained in terms of a mathematical theory, which we might try to understand, but be able to do complex, accurate calculations using, even without fully understanding. And consciousness, I think, will be answered by its simulation, by building sufficiently complex computers to simulate all the attributes of consciousness, which principally is self-awareness. So one of the differences between between philosophers and scientists is that philosophers, as I indicated, are regarded as pessimists, whereas scientists are optimists, so driving into the future, hoping to find answers to real questions rather than fake questions. And in doing so, they add to the delight of being alive. I think you can look at a rose and see that it's beautiful and just enjoy looking at it. But if you're a scientist and you're in the mood, then you can deepen your delight by asking why it is beautiful, why it has that particular color, why it has that particular fragrance, why do we respond to it as a beautiful object. And science, I think, deepens the delight in the world. So there we are, pessimism versus optimism. The expectation of answering the great questions and enjoying the universe the more we understand it.
Thank you very much, Professor Atkins, for such a wonderful opening remark. As a preliminary question of sorts, would you accept, let's say, the accusation or the description of scientism that is often ascribed to you?
What do you mean by that? What description? What do you mean by, what was the question?
As a preliminary question, how do you respond to, say, charges or descriptions of scientism, of being a proponent of scientism?
Yes, I mean, people say that we scientists are cold-blooded people, and we don't take the emotional side of science of life into account. I think that's nonsense. Well, first of all, truth might be difficult to accept, but you cannot use pleasantness to be a criterion of accepting an assertion. It has to be based on evidence. And if the evidence leads you to a discomforting conclusion about, for example, the nature of life, the fact that there is no life after death, things like that, then I'm afraid you have to accept it. and look for the way that other pleasures are deepened. And I think in the end, you have to decide whether you want to live a lie and accept assertions that are wishful thinking, like life after death, or you accept the truth and build your life on that. So I prefer to live a life based on truth rather than deception. I also think that some understand human emotion. I think science could understand why a person might fall in love with someone else. I mean, psychology, physiology are all parts of science, and our emotional reaction to our surroundings. So all of them are open to scientific investigation and elucidation.
My previous query pertained to scientism, right? And you responded by pointing out that scientists are often accused of, let's say, being cold-blooded creatures. And that's as the way I see, that's an aesthetic or emotive response to, let's say, scientism. But from a purely epistemic view, where do you think there are legitimate boundaries to the scientific method? Because philosophers will come up and say, all right, science cannot really answer what nothing is, or let's say the metaphysics of nothingness before, say, the universe started. And that's often a description. So where do you draw the line in, let's say, the scientific method?
Yes. Well, that's a sign of the philosophers being pessimists, which is, I mean, let me be clear, there is good philosophy and not good philosophy. I think good philosophy includes moral philosophy, where that a philosopher might reflect upon the nature of good behavior in a conflicting world. That's fine. And there's political philosophy, there's jurisprudence. It's when philosophers intrude into ontology and into the nature of the nature of matter that they make progress only when science makes progress. The philosophers, good philosophers, on the nature of matter, always have to catch up with the progress that we scientists have made. If they didn't follow current science, then they are not worth listening to at all. I think, though, that when it comes to metaphysics and what matter is, I think science can illuminate the kind of questions that they should address. So let's go back to the origin of the universe, which was obviously a very big question and one that will require a great deal of future progress. But science, I think, can simplify the question that should be asked. And let me just speculate here. I think when you look around, you see many things, many objects. I think there is probably nothing there at all. And what I mean by that is before the universe came into existence, there was absolutely nothing. There was no space-time. There was, let's call it absolutely nothing. I think when the universe came into existence, that nothing divided into its opposites. Let me give an example. We all know that in this universe there is electric charge. There's positive charge, there's negative charge. We also know that the amount of positive charge in the universe exactly balances the amount of negative charge. And we know that experimentally, because the force, the electromagnetic force, is so much stronger than the gravitational force that if there had been, say, more positive charge than negative charge, the universe would have blasted itself apart, because gravity is far too weak to hold it together against the repulsive force between like charges. So we know experimentally that there's equal amounts of positive and negative charge. So before the universe came into existence, there was no charge. There was absolutely nothing. So you can see that when the universe came into existence, what happened in a way that we do not understand, absolutely nothing separated into its opposite plus and minus charges. Another example of that, which is much more speculative, is that we know that there's a great deal of energy in the universe, and we can assess how much energy there is. What we do is to take the mass of a galaxy, multiply it by c squared, use E equals mc squared, and so get the energy that the galaxy represents. And then we do that for every galaxy in the universe. And we get, obviously, a fantastically huge energy. So the question is, where did all that energy come from? Now, the scientists are circumspect. And so what they do, they say, well, did we include all the contribution to energy? And that calculation did not, because another source of energy is the attraction, the gravitational attraction between galaxies. So whenever you have an attraction between entities, it corresponds to a lowering of their energy if they're close enough to interact. So now go back to the original calculation, include the attraction from one galaxy to another. That original big sum goes down a little bit. Another galaxy with another galaxy, the sum goes down again. And you can see where the argument is going. If you include all the gravitational attraction between all the galaxies, and you include things like dark matter and dark energy, then I think, and this is speculation, I think you get down to zero. So at the inception of the universe, my vision is once again of the absolutely nothing separating into equal and opposite contributions to the energy. So as you can see, in a sense, the original nothing simply separated into its opposites. And the opposites is really net zero. So there's nothing here at all, still, although it's a nothing that is a much more interesting form of nothing, being a combination of equals and opposites. Now, the reason I'm going through that sequence of thought is that it has simplified, in my view, how a scientist needs to address the question of the origin of the universe. Because if you are in a forest and you come across a heap of dirt, you might be puzzled how it got there. But if you see that next to that heap of dirt there is a hole, then it's pretty obvious. You might be misled, but I think it's clear where that dirt came from, and so the problem goes away. So I think instead of scientists having to account for the origin of energy, of charge, and whatever else, all they have to do, in my view, is to explain how absolutely nothing separated into equal and opposite components. And that seems to me to be a great simplification of the kind of question that should be asked.
That's indeed a very elegant way to describe how absolutely nothing can emerge in something. But at the same time, one thing that comes to my mind is that the original state of affairs that you're describing is quantitatively nothing. But the moment it transitions into, let's say, positive and negative charges, there is a qualitative aspect of, let's say, a certain fundamental property that is being associated with it. Charge, for instance, or energy, for instance. How do you conceive of the origins of these fundamental properties?
Yes, well, this is going beyond modern science. This is, but let's forge ahead with optimism. I think I suspect, my view, which I have explored before, but it's kind of late night discussion sort of question, is that in my view, the world, the deep structure of the world is mathematics. And so there are various pointers in that direction. One is that mathematics has proved to be extraordinarily potent in our ability to describe the universe. You can't do physics without mathematics. And so it's as though there's a very close correspondence between physical reality and mathematics. The reason that they match so well is perhaps a hint that physical reality is mathematics somehow. And I'll come back to that somehow shortly. And there are other ways of seeing the origin. I mean, a mathematician, Kronecker, said that in the 19th century, so God gave us the integers, and mathematics effectively is doing to the integers things that they weren't intended for. So if you accept that definition, then to look for the deep structure of the world, you first of all have to look for where the integers came from. And in mathematics, you can create the integers from absolutely nothing using set theory. Well, you might argue whether theory is an absolute nothing, but never mind. So you can start with the empty set, nothing at all, a bit like before the universe came into existence. And then you can think of a set that includes the empty set, and we'll call that 1. And then you can think of a set that includes the set that I just mentioned, and the set that includes the empty set, and we'll call that 2, and so on. So out of absolutely nothing, you can build the integers. And then once you've got the integers, and you do nasty things to them, you have mathematics. So you can see another analogy why the deep structure of reality might be mathematics. And then, in a sense, another metaphysical question touching on what you're asking really is, how do we how do we experience that mathematics? Because matter seems to be tangible, and we can go out there, see it, and touch it. Once again, this is high speculation, but what's wrong with high speculation? Don't think it's the truth. Just think of it as speculation. In my view, all sensation, all our senses, have one thing in common. They all depend upon touch. And it's just that the sensation of touch, and I'll expand on that in a moment, goes back to different regions of the brain where it is interpreted in different ways. So touch itself is, when proteins in the sensors in your fingers, for example, change shape and send a signal into the relevant part of the brain, and you experience touch. Olfaction, smelling. Once again, it's smelling is when a molecule fits into receptors in the nodes, and so a molecule fits into a receptor if it touches it and matches that, and its shape matches the receptor shape. So once again, from the olfactory epithelium, a signal is sent to the smelling part of the brain and interpreted as smell. Taste as well. Taste is mostly smell anyway. Hearing. It's the impact of molecules on the tympanic membrane, on the eardrum. Once again, it's touch. Vision. Well, the primary act of vision is the excitation of a retinal molecule when it absorbs a photon entering the eye and striking the retina. Now, when that photon excites the retinal molecule, the molecule changes shape and it no longer fits into the protein that is holding it. It is ejected. The protein changes shape and sends a signal to the optic centers of the brain. So that sort of touch is interpreted as vision. So you see, all our senses, I think, boil down to touch being interpreted in different ways in the different regions of our brain. So you then have to ask yourself, because we're on this metaphysical gig, really, why can you touch anything? And what does it mean to touch mathematics? And the closest I can edge, you and your listeners might be able to help me go beyond this. The absolute crucial mathematical principle in quantum mechanics that governs whether one body can penetrate into another body is the Pauli exclusion principle, or the Pauli principle, which is a statement that effectively that the wave functions of fermions must change sign when you exchange any pair of fermions, any pair of identical fermions, to electrons, for example. So there's a mathematical principle. the Pauli principle, which translates into this world as one piece of material not being able to penetrate into a region occupied by another. So, in a sense, you can see that the Pauli principle is at the basis of touch. And as I've explained, touch, in my view, is the basic sensation interpreted in different ways. So, in that kind of stream of consciousness talk, really, I'm beginning to edge towards, well, I hope that you can see that there is a possibility that mathematics can become tangible. And that is why we experience entities, physical entities in the world.
This really got me thinking
It might
about...
all be nonsense, of course, but as I've tried not to depart from a scientific worldview in going down there, and I haven't invoked some spiritual component or anything. The only words I've been using are words that you would find in any scientific textbook.
Absolutely, sir, man. Even though I'm a history student now, I did study sciences up to the, say, the A levels, and this does really got me thinking about some of the conundrums I was grappling with at that point of time. The most direct one, obviously, being whether mathematics is discovered or invented, and it seems to me that you would take the stance.
Yes, well, I think I'm a Platonist. I think, in the sense that I think mathematics is out there to be discovered, in the sense that, geometrical relations are there to be discovered, algebraic relations are out there to be discovered. So, in that sense, I'm Platonic. But what I've just been talking about, of course, goes beyond Platonic idealism. Because it says that not only is the mathematics out there waiting to be discovered, but when you discover a new country or a new element, what you're discovering is a manifestation of mathematics. So it goes beyond Platonic idealism to perhaps into nonsense, but at least it might be thought-provoking.
And I think another corollary of this would be, so the way I'd posed the query to you when you responded in how mathematics may explain how reality operates, was that I assumed that charge is a distinct property as such, worth, let's say, highlighting. But the way I understand your explanation, charge really isn't something very special. It's just another way in which this touch or this interaction is playing out. So one shouldn't really, let's say, focus, or one may not, let's say, necessarily have to put focus on, let's say, these properties, but really see them as ways in which these interactions or these forms of contacts are playing out. So would you agree with, let's say, that sort of an understanding of, say, the fundamental properties?
Yeah, well, let's think a bit about fundamental properties, and let's get away from this mathematical model for now and try to be a little bit more down to earth. Mass, first of all. A mass is localized energy. So when people go on talking about the equivalence of energy and mass and quote E equals mc squared, it's really a little, or they also thinking about nuclear power. They're talking about the conversion of mass into energy. I think that's incorrect. If you take the view that mass is a measure of how much energy there is in a localized region, then in a nuclear power station, you're not converting mass to energy. You're releasing energy from its localized part of the world inside an atomic nucleus into the surroundings. So it's only energy. What energy is another question, of course. And we know that mass has, that is localized energy, has the ability to distort space-time. And that's really the essence of Einstein's general relativity. Spin. Electron spin. That's a tough one. Because although spin to some extent looks like angular momentum, the intrinsic angular momentum of a fundamental particle. It behaves differently. I mean, an electron has to turn around twice to get back to where it began, things like that. So, although the algebra is the same, let me put it another way. Well, one of the maybe old-fashioned ways of thinking about the distinction between a proton and a neutron, both of which, one of which has got positive charge and the other one zero electric charge, but have approximately the same mass, suggesting that they're very, very closely related particles. One way was to say, well, let's think about a property called isobaric spin. And when the isobaric spin points up, it means you've got a proton. And when it points down, you've got a neutron. And so an isobaric spin behaves the same algebra as angular momentum does. So should you think of the difference of having a charge or no charge as a manifestation of angular momentum? But the algebra is the same, but the physical emergence is very different. So when you go back to the electron and its spin, maybe there are two kinds of electrons, both with the same negative charge, but one has got, let's call it spin up, and the other one has got spin down, and these are two different particles. They're not the same particle with angular momentum orientated differently in space. I mean, they've got all the same algebra. So mathematics could be very deceitful. And whether the universe, the biggest deceit of all, of course, is that maybe if you accept my notion that there is nothing out there after all, that it's just a nicely reorganized absolutely nothing. Then the biggest deceit of all is that there's absolutely nothing, conning us into thinking there's a lot of something. So I think, so not only does the universe have no purpose, it's the biggest deceit you can imagine. But that's one of the joys of science. We're talking to your listeners here because they're interested in science. One can have these trips of fantasy, which might not be fantasy. They will only be proved to be not fantasy when experiments have confirmed any predictions that they might make. I made a prediction once about the emergence of the universe out of nothing. And the prediction is true. It's a very banal prediction, but if it were not true, it would be catastrophic. And the prediction is that there is only one dimension of time. Now, it's true, all right? No one's going to deny that. Well, some people might, but but I think there's very compelling evidence that there's only one dimension of time. Now let's see why. If you have a bit of space-time that is one-dimensional, you can't turn round, because even the word round no longer has a meaning. So if you've embarked upon a journey, you're stuck with going in the same direction. You can go at different rates, certainly, but you can't turn round. And I think that time distinguishes opposites. You can think of an antimatter, really, that you can picture an anti-electron as an electron moving backwards in time. Okay, so the distinction between opposites depends upon there being a dimension of time, and the stability of the distinction between opposites also depends upon that one dimension, because you can't turn around. Once you've got that distinction, you can't undo it. So going back to the emergence of the universe from absolutely nothing, because opposites emerge, you need time for that distinction to become established. And once you've got it, you can't lose it. So the universe must have one dimension of time. Otherwise, it would have collapsed as soon as it was formed. So you see, you can make profound predictions. String theory seems at the moment to require one dimension of time and about 11 dimensions of space. But there's no evidence for that yet. But maybe there will be one day. When there is, we can accept it. I mean, science, I suppose, if I can go just a little bit further down the same path, is well, the experiments to confirm these very cosmic predictions are becoming so difficult to do, and requiring, the gross national product of every country in the world, every other world that might be inhabited as well. So there might come a point when experiments are no longer feasible. They can be conceived, but not performed. And we might then have to rely upon science, showing that it's been amazingly self-consistent, with concepts flowing from everywhere, all melding together into a consistent, all-embracing theory, that although we can no longer test it in detail, its major predictions, we scientists of the far distant future might have sufficient confidence to say that's it. That is the answer. What we'll have to do then, I think, because it'll be very boring doing science, because science will be at the end. There'll be plenty of applications, of course, making us all immortal being one of them. I'd rather look forward to that case. That we might have to have robots, because ordinary scientists would not have the patience to be on the lookout for deviations that we don't expect to happen. You can't get a PhD by saying nothing happened at all. I've stood looking at this instrument for 5 years, nothing happened. Can I have my PhD? And so on. But I think we'll have to generate a class of robots. Robots are infinitely patient, at least the ones we can conceive of at the moment. And just have them as outposts in the intellectual cosmos, as it were, looking for deviations from prediction. And perhaps in 1 trillion years, one of them might pick up something, and we have to say, well, it was all wrong anyway. But so the scientists currently are in a wonderful, vibrant, flourishing era. I mean, science didn't really flourish until Newton came along, and once again, going back, applied mathematics to nature and found that it worked. And then the enormous progress that was made with understanding the origins of life, the development of life with Darwin and natural selection. Then the understanding of the molecular biology of life with Watson and Crick and DNA and a modern molecular biology, which turned biology from just nature walks, which I did at school, to a part of the physical sciences, because biology is chemistry, and chemistry, I accept, is physics. And we're in the midst, theoretical physics is in a bit of a slow episode at the moment, but think of all the progress going on in molecular biology, in material science, in mathematics. It's a highly active area. And maybe you and all your colleagues are alive at exactly the right time to be in the midst of this fantastic achievement. Humbling achievement in a way that we humans have stumbled upon a way of discovering the nature of truth, the nature of the world. Just hope that we can survive long enough to enjoy it.
Your optimism is really something that's very reassuring. But
Yeah.
at the same time, while reading about a few, how should I put it, voices of dissent, perhaps, um, there has been a lot of, say, dissatisfaction with some of the, let's say, popular strands of science, because I understand that a lot of scientists, while engaging in scientific communication, in an attempt to, let's say, uh, establish resonance with the public, oversimplify or inflate the importance of, say certain concepts. For instance, I distinctly remember string theory being something very fascinating, and it was only later that I got to know about a lot of the incertitudes that it rests on. For instance, when Lee Smolin said that, completely dismissed string theory as saying that it makes no testable predictions, it has no coherent mathematical formulation, and that there has been an increase in, let's say, the number of dimensions, with, say, somebody saying there may be 5 dimensions and 11 dimensions, and then adding on more dimensions. And at the same time, I still find string theory being very popular in, say, the popular understanding of the science. What do you think about Do you share this, say, pessimism
Sorry, your sound is
vis-a-vis
broken
string
up
theory?
again. Yeah.
Am I audible now, sir?
Sorry, say that again. String theory. Was it?
Right.
Yeah. Oh,
Um,
I think it's fascinating. I mean, it's who knows whether it's true or not, but it's string theory is certainly very compelling because it is an example of self-consistent mathematics, seemingly accounting for a wide range of phenomena, although it hasn't been tested really. It might be true. We don't know. Yeah, or some version of it might be true. But I think in my heart I would like it to be true. But one's heart is not a good litmus test for for scientific validity. So let me just simply say I would like to think it will turn out to be true. Yeah, and I think scientists, maybe taking up your point in a slightly different way, scientists have a duty to share their insights with the general public. After all, a lot of their work is funded anyway through taxation. And so the general public is paying for a lot of the research that is done, even not necessarily directly, but even when they buy something in a pharmacist, then they are contributing to the profits of a pharmaceutical society, company. So they are paying for the research that led to that particular pharmaceutical. But it's broader than that. I think nation states also support the arts with as they are right to do, because it's a part of the cultural milieu of the society, that there is art, music, plastic arts, literature available to the population. That makes it all part of the pleasure of being alive, basically. It's a shame that it goes on armaments too, but that's another story. But I think also the other obligation for science is not just that people have paid you to do it, but it has deepened understanding. It drives back, in my view, my perhaps over-hopeful view, it drives out religion. I'll come back to that in a moment, and replaces it by truth, valid, publicly shareable, uncontestable, international, cooperative understanding. So it's good for the world and for individuals to be closer to the truth. Now, let me just say about driving out religion. The trouble is, religion is much easier than science. Religion can get away with saying, well, God did it. And the listener says, oh yeah, thanks very much. I always thought that was true. And they go off so happily into the sunset. Whereas science, if you say, well, I'm afraid this is going to be rather boring because I've got to take you through a chain of argument. I've got to start with something you appreciate, take you through some biology, maybe some chemistry, maybe further still into some physics, and who knows, into mathematics. So the listener has got to invest a lot of attention into comprehending science. Whereas in religion, it's obvious. You get instant satisfaction because when you don't have any work to do, you just blindingly accept what you're told. So what we rational people are up against is impatience, because you need to be patient to pursue a scientific explanation. And so it's very important that we have to, if we go out into the world to trying to explain science, then we have to ask for patience, or we have to find ways that shortcuts. There's a shortcut around impatience. But I think that's what we're up against. Instant gratification from religion. Hard work, but rewarding hard work through science.
Very true, very truly highlighted about, say, the challenge of instant gratification that scientific communicators are up against, and how we should, let's say, not engage in oversimplification to, let's say, bypass this instant gratification. Another theory which comes to my mind when I think about how scientific communicators sometimes, not all of them obviously, but sometimes, let's say, offer very fanciful models, is the multiverse theory. Now, when I read your book, Conjuring the Universe, the one thing that struck out to me is that it doesn't multiply entities beyond necessity. It's a very simple exposition of how the universe could have occurred without, say, bringing in other parallel universes, or let's say bringing in strings or other fundamental entities. A very simple exposition. But then if you go on to YouTube and you find scientific communicators, you find very, very fanciful explanations. So sort of a follow-up to the previous question, how do you view, say, attempts to come up with theories such as the multiverse theory? Is it really a good way to approach science and scientific explanation?
What was the question?
Do you think that theories such as the multiverse theory, are an appropriate way to, let's say, engage in scientific explanations, given the fact that theories such as the one that, or explanations such as the one that you have offered, do not bring in gratuitous entities such as a parallel universe into the picture?
I'm still not quite sure what you're asking, but are you saying that I'm taking a very Western view, a Western cultural view, and that I should?
No. I was asking, in your explanation. At least, okay, let me put it this way. I think Sir Roger Penrose criticized the multiverse theory by saying that, why are you bringing in other universes into the picture, right? So why do you need to bring in other universes? And let's say, what's the difference?
Oh, I see. Okay. You mean the multiverse?
Right. But then your theory doesn't do that at all. It's a very simple explanation of, say, how the universe may have come across. And I think its elegance struck out to me. So, I mean, as a scientist, how do you view such, let's say, fanciful explanations of bringing in multiple entities which you can't really account for to explain the universe?
Well, let's put it this way. If the mathematics of the emergence of the universe, our universe, indicates it, then we have to take it seriously. And so I have proposing that there are many universes is obviously almost religion by saying that there is an answer out there, but I can't demonstrate its truth. I will accept it and so on. But if it turns out that there are many universes predicted, then we must cautiously look for manifestations of it. Now, it could be that the following is a little bit of indication there are more than one matter and antimatter in this universe. Antimatter. If what I said some time back about everything being really nothing, why is there that imbalance? Now, if you've got many universes, then some of the universes will have more antimatter than matter. Some of them will have more matter than antimatter. And so if you expand your conception of a universe to embrace all conceivable universes, this one and all other ones, then it all averages out to zero again. So you could say, because there must be nothing here, because nothing can come from nothing, then if you find that there is something here, then there must be other universes which enables it all to cancel out. So there's a tiny sort of rather metaphysical argument, I suppose, but so the idea of many universes can be very useful. I think I know where they are, actually. But I don't want to go down this rabbit hole at the moment. Here's another wild speculation for you to reflect on. Suppose the universe could be regarded as a collection of points. In this universe, we know that this point is near that point, and that point is a long way from another point. In other words, this universe has a metric on it, which enables us to say what is nearby and what is distant. Now, take the same set of points and impose on it another metric, so that what these points A and B are now cosmic distances apart. And the one that I said was a long way away is now, according to this metric, is very close. So you can see you can build different universes from just by having a different interpretation of what point is next to what. That is, the different universes could have just different metrics. So they could all be assembled from the same points, but appear to us, this one that we actually inhabit. But you see, in other words, this universe would be pervaded by all the other universes, because it's all made up of the same points. It's just that our perception refers to the metric that we call this universe. So that's as wild a speculation as I'm prepared to do. But once again, I hope you realise that although I'm speculating, I'm not running off the tracks, the scientific tracks. The words I'm using, I hope I've tried to keep them as words of the scientific lexicon.
Absolutely, and I hadn't thought of that before. I mean, the fact that this argument about something coming from nothing and that something just being a more complicated form of nothing is something that can also be extended to the level of the of a supposed multiverse in case
Yeah,
we are
yeah,
willing to apply that. I mean,
yeah.
I genuinely hadn't thought of that.
It's a long way from physical chemistry, of course. But if I could just, I think we're coming to the end shortly. At least I have to go soon. If I can say that um, I sometimes wonder whether I should have been brought up as a physicist or whatever. Um, uh, I, on reflection, I'm glad that I went through the chemistry road and became a physical chemist, or chemist, per se, because it is it's widely said, and in fact is widely true, that chemistry is the central science. In order to do chemistry, you need to appeal to physics for the explanations, quantum theory, thermodynamics, and so on. So, by being a chemist, you need, at least my sort of chemist, you need to be able to understand physics to some extent. And you're driven, because chemistry is all about the manipulation of matter. You're driven also to understand what matter is. So you're driven deep into fundamental physics as well. But then on the other side of the chemistry's coin is biology, and the fact that increasingly biology is chemistry through molecular biology and so on. What someone said, a biochemist really, once said that nothing can be understood except in terms of evolution. That is true in terms of phenotypes and phenomenological biology, but nothing can be explained in biology except in terms of molecular biology, which is an application of chemistry. So by being a chemist, not only are you reaching down into the foundations into physics for your own understanding, but you're reaching out for application into biology and inorganic biology, that is material science, for the applications of your craft. So I'm pleased to have made a career that centered me in the middle of science.
I think that's a wonderful way to describe the vantage point of chemistry. And sir, do you think you have time for one last question? Because I know we are close to the 90-minute mark.
Yes.
Based on what I have understood from my time studying physical chemistry and statistical mechanics, as it's called here, I've often thought about the limits of determinism in, say, understanding the universe, because randomness, at least to me, whether it is something as mundane as, say, Brownian motion or something which is as profound as entropy, it seems to be a very, let's say, recurring feature in the way the universe operates. At the same time, even when we talk about issues such as consciousness, for instance, and you have a lot of people who deny free will and who take a very deterministic understanding of science, I'm sort of trying to understand how we may understand this dichotomy between determinism and, say, randomness. And is there agency at all, or human agency at all in this?
Yeah. I see a question just popped up about Boltzmann and so on. But I gave a talk in London a couple of weeks ago on the second law of thermodynamics, which is one of my favorite laws. And where you have effectively the world being driven forward by collapse into disorder. But it's in such a the world is such a complex, interconnected place that even though matter and energy is spreading in disorder, the interconnectedness means that order can emerge here and there. And so you and I are local abatements of chaos, effectively. We're driven into existence by the world dispersing in disorder. And mental activity as well is just driven. That's why we have to eat. We have to eat in order to have energy to disperse. And then we tap into that energy, that dispersing energy, and it drives random synaptic processes into thought. And when it comes to determinism and free will, I think we just have to accept that the brain is such a complex organism that it's impossible to predict the outcome caused by any given stimulus. So the stimulus effectively gets lost in the complexity of the neuronal structure of the brain and comes out as an action or a deed or a thought, which it is impossible really in most cases to predict. At a kind of observational level, I don't have any trouble with free will. I think also quantum theory is, in my view, deterministic, although everyone says it's not, but it's probabilistic. I think I don't have time to go into this, but the uncertainty principle is a very important principle because it tells us that Newton got it wrong. He and his classical followers thought that they could describe the world in terms of positions and momenta. Quantum mechanics says if you try that, it screws it up. You have to choose between describing the world in terms of position of every particle or in terms of the momentum of every particle. If you stick to one language, everything is deterministic. Whichever language you choose, either one is deterministic. It's when you try to impose kind of farmyard upbringing that we expect position and momentum to be joint parts of explanation. And we try to bring these two conflicting languages together, that everything falls apart and it looks probabilistic. And the uncertainty principle effectively is a statement saying, choose your language, don't mix them. And I think you can look at a lot of things in quantum theory and see that it's really a clash of languages. And that's why people like Bohr and Einstein couldn't come to terms with quantum theory, because they were insisting on imposing classical views. They didn't have the courage to divest themselves of their pasts.
And I think this is a wonderful way to end because